Good morning, and welcome to my talk on avoiding disasters with strongly typed C++. Let's start with putting this up. In other words, the sooner we find bugs, or the later we find bugs, the more expensive and hard it gets to fix them. My name is Arno Lepisk. I live in Stockholm, Sweden, where I work as a software engineering consultant for a company named HiQ. I've been working with C++ for a little bit more than 12 years in fields such as defense, datacom, telecom, video games, industrial applications, and such. When do we want bugs to be found? One could argue never, because we never write bugs, right? Has anyone never wrote a bug? Great. Sure. The comment was that you don't write bugs, they just appear. What if we find bugs in production? That's expensive, right? If you build embedded systems, you may have to do recalls, or at least send out patches. It affects your customer relations and such. In extreme cases, have you heard of the Mars orbiter? That was a disaster in production. Okay. We can find bugs in quality assurance. That's good. System testing, if you have automated system tests, even better. Unit tests, do everyone use unit tests? What about if we could find bugs already at compile time? So bugs never even get to actual code. I'm going to talk today about a special kind of bugs that come from mixing up types and using types in the wrong way. Type safety. What's type safety? One definition is that the language is type safe if it prevents type errors. And by that we mean undesirable behavior due to type incompatibilities. So, is C++ type safe? Let's look at some examples. This is the first example. We have a function that sets a node name for a node identified by an int. And if we call the method and mix up the operations. So we try to set a name or a string where the method expects int, or vice versa. We get a compiler. Great. But we have another method that takes two ints. Disaster. Because even if we named our variables size and int, the compiler doesn't care. It just says, it's an int. Who has made mistakes like this? Okay, what can we do? First thought, well, let's use the typedef or a using clause. Does that work? No. And why? Because the typedef only creates an alias for the type. So the compiler still sees int, even if we call it a different name. Let's put our values into structs. Now the types are distinct types. So the compiler can warn, or even it gives us an error if we mix the types up. Great. We're there. As you see here, these are structs. So we have to use the curly brace initialization. We can fix that. We add the constructor. And this is very much pseudocode, or it actually compiles, but if you do this for real, you should add more stuff to actually make it behave sanely. Simon Brand made an excellent talk yesterday about type wrappers. Check it out. Okay. But now we have constructors. Maybe we want some other methods. And it quickly becomes quite a lot to write if we have to do this for every single type we use in a program. Enter templates. If you look at this template code, you see that we have a type named tag that actually isn't used anywhere in the type. So it is just what we call it. It's a tag. So we can make distinct types by having distinct tags. This creates two identical, or not identical, it creates two distinct types that for every other aspect are identical. Now how about performance for this then? We put it into the compiler explorer. We have two methods. That one takes an ordinary int and one takes a wrapped int. And the generated assembly is the same. Provided that you turn on some optimization and use a reasonably recent compiler. And here's another example where we take in a strong int and pass it on to a legacy function that takes an int also. Because the representation of a struct that only contains an int is the same as an int. Great. But say that we actually want something that behaves like an int, that we can add, subtract. So let's create a new template called arithmetic strong int. And why don't we just extend the first one? Well, because sometimes you don't want an int-like behavior. So how many have used the raw socket programming on Unix system or Linux system? What represents a socket? It's an int. What's reasonable to do with that int? You pass it to the socket functions, yes. But adding to it, so for that you don't want arithmetic. So let's make these add the operators. But this quickly starts to get rather much writing. So someone must have thought about this before. So quick Google search for strong typedefs, it turns out up quite a lot of results. I jumped too far, sorry. So I picked two, Jonathan Boccar's name type and Jonathan Müller's type safe library. And let's see how we can use those two libraries to do what we want. They work in a bit different ways. The name type library works like the one I showed recently. You use a tag. So for this, we can use, we create an int. This has a skill or something called comparable. So this adds the comparison operators to this type. And the same for typesafe. That uses a bit other constructs. There you create a new struct and inherit from a base type for all strong types, or strong typedef. And then you use CRTP as a curiously recurring template pattern to forward your own name down into the library. And then you have to use the using construct to make sure that the constructors and so are available. Crystal clear? So let's make an int again. For the name type library, again, we say we want an int. We use the tag, myInt tag, and specify which operations we want. Printable, it's for making it possible to output it to an O stream. Addable, subtractable, multiplicable, and comparable. No division, for some reason, in the version that I checked out. We'll come back to that. And for the strong type lib, we inherit from the first from the base strong typedef, and then from output operator, integer arithmetic, equality comparison, and relational comparison. And there we get something that more or less behaves like an int, if we do normal arithmetics on them. No bit operations and such. Okay. And how do we use it? If we define it in this way, we can use both ints interchangeably. So we can create two ints with values, and we can add them. And then we can use static assert to check that the type actually we get the same type back. And we can output. But if we try to add an ordinary int in the commented out code, we get a compiler. That's what we wanted, right? Sometimes we need to get the underlying value out, and there the two libraries differ how you do it. For name type, you get a member operation called get, then you get it out. And for the typesafe, you get there's a freestanding function get that you can use to get the value out. This becomes a little bit important later when we do adaptions for this. Okay, and sometimes we need to combine types. Here we showed we can add two of these myints, but sometimes we want to interact between types. Say, if we want to calculate a price from a base price and an amount, then you need to multiply these two together and get a new price. So, how do we do this? First, a table of what kind of operations we would like. So we can add two prices, get a price, subtract two prices, get a new price, the same with the amount. Multiply price with price, doesn't make sense, right? Skip that. And the same thing, multiply an amount with an amount, doesn't make sense. But if we take a price times an amount, or an amount times a price, we should get a price. So how do we accomplish that? In typesafe, it's already there. We add a new skill, mixed multiplication, where we say that the price you should be able to mix it with an amount, and then it renders a new price. For name type, there actually isn't anything like this built in, but it's easy, or for some value of easy to add. So we add a mixed multiplicable skill. And all of these skills for this are implemented like this. Here we have added an outer template. So we say, if we read this from the inside out, we add an operator star, which takes self, and the template sized, template M, other, gets the underlying value, and multiplies them together and returns a t. And t in this case is the type we have. And we have to do this twice because we want to be able to have the operators in both ways, like price times amount and amount times price. And yeah, and there's an added helper function called getValue that actually, if you put in a name type, it uses the .get operation to get the type, and if you put in a plain value, it just returns the value. We'll come back to why that's important soon. And now we use the skill like this. Mixed multiplicable amount, colon, type, because the inner class is called type. So. Next, we have an example of positions and offsets. You have a position, and then you have something else a bit away. Then there's an offset between them. One place this comes into standard C++ is you take pointers and pointer differences, for example. Here's the tricky part, in this case, that we have to take two positions, subtract them from each other, and render another type, the offset. How do we do that? Name type, we looked at name types recently. It's about the same method. We have subtract to type. Didn't come up with a better name. There's two hard problems in computer engineering: cache invalidation, type naming, and off-by-one errors. Subtract to type. So here we subtract the two underlying values, put them into the enclosing type, and we're in. And then we use it in a manner very similar to the way we did before. And here we also use, I've added mixed addable in a manner similar to. All this code will be available for you. Look at. And here also you can see I used mixed multiplicable with a basic type, so you can actually multiply offsets with plain ints. In typesafe, it's about the same method. It's just a bit like, what do you call it? Implementation details. And I've cut away the no except stuff because it's just the same thing repeated once again. And here we can use it again. Subtract to type, you see that on the next to last line. Should have been highlighted. Okay. And then we can use this like this. So we create the position, and then we can create an offset by subtracting another position from that position. And if we try to add two positions, we get a compile error. No errors there. And here when I sat and developed this, after a while it got very tedious to see which files were supposed to compile and which weren't supposed to compile. So I wrote a helper that actually checks if there is an operation plus between position. You can use static assert for this. It's here. I'm not going to go through this. It's here. Look at the videos later or check out my GitHub. Links will come. Now, length. This is what actually started my interest in this. Because my background, educational background at least, isn't really computer science, it's engineering physics. And there we often, when we calculate stuff by hand, the standard method to doing it, checking is dimensional analysis, and from that we get on to it. Okay, what's wrong with this method? What do we mean by length? Meter? What? Units. Units was the comment, yeah. Precisely. What unit is the length? Is it meters, millimeters, feet, yards? We could create a type like we did before, saying it's meter t. But then maybe someone else is more convenient, is more accustomed to counting in feet. And then you have to start making conversion operations between them. And then you have someone who wants millimeters. Then you have 2 to the 3rd power, and so on and so on. So the number of conversion operations grow exponentially. But let's think again. What do we have? Well, in the C++ standard, we have the chrono library, which does about this thing, but with time. You can create seconds and milliseconds and add them together and get correct results. So in this example, I create one variable with seconds and then convert it to milliseconds. And that's the ratio 1000 between them. So let's just hijack the chrono lib, define 1 meter as 1 second, and so on. No. That would take away all the typesets, because then we could add seconds to length, or time to length, and that just doesn't make any sense, and that's how, bad things happen. But we can look at how this duration class is implemented and maybe reuse it. This is the geist of the duration, or the chrono duration defines. You have seconds, it's a chrono duration of, the standard doesn't actually say it has to be int 64, it just sets some kind of lower bounds on how many bits you have to use. The 2 implementations I looked at both use int 64. And then we have milliseconds that use something called milli. What's that? STD ratio. How many of you have used STD ratio? Good. For everyone else? It's a standardized way how to do rational arithmetics at compile time. So what this means is that milli is a ratio 1 through 1,000, 1,000. So 1,000. And it shortens the the fractions automatically, if you want. And it defines different arithmetic operations on such fractions. So how can we use this? Let's start our new own length class. We define a length. We let the template take care of which underlying type we want, ints or doubles or vectors or whatever. And then we use a scale. We default the scale to 1. And then there's lots and lots and lots of methods in there. Then we can make some defines for this. We say that a meter is the base type, a millimeter is the 1000, and we use the standard provided prefixes, milli, kilo, and so on. And we can also define inch and foot and mile. If you start counting on them, you see that 1 inch is 25.4 millimeters, and if we put it into whole numbers, that becomes that. So it's an exact representation of an inch in meters. And then we can add operations. We can add these together. And for the case when the ratio is the same, in this example for plus, it becomes very easy. Because the length, 1 meter plus 1 meter is still a meter. What happens if you have different underlying types? What type should that render? If you take 1 meter in ints and add 1 meter in double? One could think. No, but we can actually, what happens if you take a basic int or a built-in int and a built-in double and add them together? Precisely, the answer that the int is promoted to double. And how can we do that? Use the decal type. So this will be a meter of double. Yeah, but it behaves, the comment was this can be type and safe. In a way, yes. On the other hand, it behaves like we expect it to be. Or at least as I expect. If I add an int to a double, I expect a double. It will be promoted to whatever an int plus a float becomes, thanks to the decal type. If you have different ratios, then it becomes a bit more complicated, because we have to bring the values to some kind of common. If you remember from school how you add fractions, you have to bring them to a common denominator in order to add them together. And then that we do by taking the greatest common divisor between the two fractions, and that's that formula. And then we can add 2 meters to 3 feet, and then we get a very strange value, because feet are expressed as 381 through 1050 meters. The common ratio between those is 1 through 1250. So if we try to output this, we get this strange value. Okay, show how we use this. But we can convert it back to something we actually know how to comprehend. And why I use this a bit strange values is because it becomes exact. 5 inches plus 8 centimeters is exactly 207 millimeters. And that's very convenient if you try to do the checks with static assert. We can add some syntactic sugar to this, literal type, and then we can write things like this. Next thing, dimensions. I showed addition. Subtraction is the same. But we might want to multiply two lengths together to get an area. Multiply it with a length again to get a volume. And even take a length through a length to get a scalar or some kind of scale between them. How do we do that? Well, we add a dimension int to our length. And now we can addition between this new length is still the same. The dimension has to be the same because it doesn't make any sense to add a length to a volume. But if we multiply two lengths, we get dimension lengths through the second power. That we can do by, if you check the second part of this slide. And in the same time, the scales are multiplied together with the ratio multiplying method that I discussed before. So then we can do something like this. Add some fancy output operations, and we can multiply 3 times 4 feet becomes 12 feet squared, or 1 point blah 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 meters squared. All transparent. Next step, physical quantities. In the same way we can tell length times length to get an area. We can take length through time to get a velocity. Or velocity through time to get acceleration, and so on. How do we do that? We expand our length, and now I call it unit instead, with 3 numbers for dimension. And we can, in the same way with length, we can make this. And now we can define our types. Length, like this. It's a unit of int. Length to the first power, mass and time to the 0th power. And area, we take the second power, and then time or velocity, we get the negative power. You can also add constants with this little trick. Oh, there's a line missing. There's a templatized struct somewhere up before this, and then we specialize it for ints and for doubles. And then we can pick out G in this part, which is the acceleration towards, And then we can use this like this to calculate this velocity. And then there are other units. If you just think about physical units, we have like current for electricity. But temperature is tricky because it's zero temperature is different for different temperature scales. So you have an offset. And now things are getting complicated again. What have we done? Yeah, boost units. How many have used boost units? We can calculate voltages, power like this. Take a voltage times current. Very nice. And you can do the same thing we did before with length. It's a little bit more writing, but the boost unit, you can also make your own units. One example, if you might remember my price example. Often you have prices expressed in price per volume, price per length, or price per weight. So there, for example, you could make your own types of that. The difference with boost units is that it doesn't do all this automatic conversions. You have to not cast it, but you have to put it into, if you want to convert foot to length, you have to explicitly write the quantity length of the number of feet. Some links to the code I've shown. And as I, like many programmers, like to reinvent the wheel, I did my own safe type implementation as well. Is there an S type? Some conclusions. I think that by using these strong types, you can, without actually any performance hit, make your programs more safe. If you find there is a performance hit, you could always use the safe types in debug builds and then define them away and use the basic types in release builds. That shouldn't be necessary. So please try them, so you might avoid some disasters. Thank you. Any questions, please, at the microphone.
Yeah, I was just curious if there are any issues, like ABI issues, like between debug and release on Windows. I know Linux doesn't usually have those problems, but...
I'm not familiar with Windows, but if you do, you define them differently for debug builds and release builds, then yeah, there will be ABI issues.
Sure.
Because yeah, you have ODR. I think you get ODR violations because you would, if you mix release and debug build stuff.
Can you address like overflow of an int and that kind of thing?
Yeah, this doesn't handle that per se. If you want that, you would need some kind of safe int implementation. What's it called? It's called safe math or something like that. I know there's another talk about that later this week. So This only handles conversion errors, like it doesn't handle overflow. That's the same as you would have had by using the plain types. Anyone else? Okay, thank you for coming.